onto the binomial distribution, we want to show that if A, B lie inside the AB region for the binomial distribution, then QK, defined using the recurrence relation, uh, gives rise to a binomial distribution. Now, when we say let AB lie inside the AB region for the binomial distribution, what we mean is fix an A that is smaller than 0. And then we also want to construct B so it lies inside the region. So we need to pick a natural number n and let B be given as minus A multiplied by n plus 1. So now we've picked an AB inside this region. The first thing we will show is indeed that the support of QK is finite. QK has finite support. And that's important to show because that's one of the key characteristics of the binomial distribution. And what do I mean by finite support? It means that QK is only greater than 0 on a finite number of points. So the specific step from which the QKs become 0 is actually n plus 1. And the reason we can see this is, well, if we look at Qn plus 1 and plug into the definition A plus B divided by n plus 1 multiplied by Qn, well, then the n plus 1 and the n plus 1 cancel, and then the a's cancel, and then we just get 0. So in turn, this implies that Qn plus 2 will be 0, Qn plus 3 will be 0, and all the QKs will be 0 for all the k's that are bigger than n. Because when I calculate Qn plus 2, all I do is I take Qn plus 1, put it inside the formula, and multiply by something. But Qn plus 1 is 0, so the next one will be 0, the next one will be 0, etc. So now let's take a look at how the point probabilities look. So QK, we want to show that in some way they look like the point probabilities in a binomial distribution. So let's just write up QK is, well, actually, first we should say let K be smaller than equal to n, since QK is 0 otherwise. Then QK is equal to A minus AN plus 1 divided by K multiplied by QK minus 1. And that is equal to, well, I can take an A outside, and then I have 1 minus n plus 1 over K, QK minus 1, right? The next thing that I can do is to put everything inside on the same fraction. So I have K minus n minus 1 divided by K, QK minus 1. And then I can take a minus outside, and I have minus A multiplied by K, so multiplied by, what do I have? Minus A multiplied by n minus K plus 1, or n minus K plus 1, or if I put the minus parentheses on, it will look like this. And just in a second, it will be clear why we're doing all of this. So I just tried like rewriting this in some different ways because I personally hypothesized that it might be useful. We don't know yet if it might be useful, but anyways, now we have some different ways that we can look at QK if need be. So we can try and look at how Q1 looks in terms of Q0 first. So that is minus A and then multiplied by n minus 0 divided by 0 divided by 1. So it's minus A n multiplied by Q0. And then I have Q2 which is minus a n minus 1 divided by 2 and multiplied by q1. Now, when I plug in the value of q1, what I get is minus a squared multiplied by n minus 1 multiplied by n divided by 2 multiplied by q0. I can kind of just carry on a little bit and see if I can spot a pattern here. Have minus a multiplied by n minus 2, 3 minus 1, so which is n minus 2, divided by 3, multiplied by q2. I plug in the value of q2, and what I get is minus a to the third, n minus 2, n minus 1, and n divide by 3, multiplied by 2, multiplied by 1, q0. And I could kind of go on, but I sort of get the feeling that qk might be equal to minus a to the k, and then I have n minus k minus 1 multiplied all the way down to n divided by k factorial multiplied by q0. So my question is kind of, is this true? And the answer to that is, well, yes, we can try to show that using induction. So let's try to show that it is true for k equal to 1. Then we just plug the value 1 into k and see if it gives us the q1 that we got up here. So this is the induction proof. I'll give it another color. Induction proof of star, and we'll call this star. Okay, so q1 is equal to minus a to the first multiplied by n minus 0, which is just n, divided by 1 multiplied by q0. So it's true for k equal to 1 because we see we get the same as we got up here. Now assume that star is true for k minus 1. Show that then it holds true for k. Well, qk, in terms of q minus 1, we can look at the formula we had up here. Well, in terms of q minus 1, qk minus 1, it's minus a multiplied by n minus parenthesis k minus 1 and divided by k. Multiplied by qk minus 1. And we have what qk minus 1 is, so we can plug that in. So it is minus a multiplied by minus a to the k minus 1 multiplied by n minus, so it is k minus 1 minus 1, so minus 2, all the way down to n. Should I do this on a new line? I think I'll do this on a new line. So let's just, I have minus a, right? And then I have the minus a to the k minus 1. And then I have the n minus k minus 1 from this formula. And then for the formula for k minus 1, it's n minus k minus 2, and so on and so on, down until, or all the way up until n. And then we have this divided by k, and the one on top for k minus 1 is k minus 1 factorial q0. And, well, this just gives us what we want, right? That it's minus a to the k, then n minus k minus 1, multiplied all the way until n, divided by k factorial multiplied by q0. So that's pretty awesome. Now we found an expression for now we found an expression for qk in terms of q0. Now, one last thing that we can kind of do is just rewrite this expression a little bit and notice that in fact this is n multiplied by n plus 1 and so on and so on, multiplied by n minus 1 and so on until n minus k plus 1 divided by k factorial multiplied by q0. And let us just recall the definition of the binomial coefficient, which is here. And what we do is we just recognize that this is exactly minus a to the k multiplied by n choose k, q0. So now we have that qk is equal to this. Now let's take a look at what q0 then must be based on our knowledge of qk. So we know that the qk's have to sum to 1, right? So since this is true, then we know that 1 is equal to the sum of the qk's, which is then equal to q0 multiplied by the sum minus a to the k n choose k for k equal to 0, for k equal to 0 up until, well, let's just see. The qk's are only expressed as such up until n. And after n, they will just all become 0. So this here, we should also check if this is true for q0. For q0, this is just 0, 1, 1. Okay, so this is true. So we know that this holds true. Hence, q0 must be equal to whatever this sum is equal to the minus first. Now, recall the binomial theorem that we have from up here. The binomial theorem says that if we have some kind of sum involving a binomial coefficient, then we can write it into a polynomial of some kind. So let me just write up the binomial theorem here, that a plus b to the n is equal to the sum from 0 to infinity of n choose k, and then a to the k multiplied by b to the n minus k. This in the integer case, where n is just a whole number, then we can just plug in n up here, because for all k's that are greater than n, this binomial coefficient is just automatically 0. So this is equal to the sum from k equal to 0 to n choose k, a to the k, b to the n minus k. Now we may use this formula to determine what q0 is. And the reason why we may use this formula to determine q0 is because we recognize our a to be actually minus this a, and our b to just be a 1 to the n minus k. So what we get using this formula is that q0 is equal to 1 minus a to the n, and then to the minus first. Phew, okay. So the next part of this requires us to kind of figure out what, uh, well, it requires us to kind of figure out how this works inside how can we somehow recognize a binomial distribution here, right? Okay, let's just rewrite this. So we have 1 minus a to the minus first to the n. Essentially, what we also have, since we have expressed the qk's in terms of the q0, qk is equal to this thing in terms of q0. So I'll also write the qk down. Qk is equal to minus a to the k multiplied by n choose k multiplied by apparently 1 minus a to the minus first to the n. So now we're kind of trying to see how we can make everything work out. Wow. Okay. First of all, we can say, well, uh, the first parameter should be n, right? So we're trying to figure out how can we write this up in the shape of probably something that has to do with n choose k, p to the k, 1 minus p to the n minus k. Can we do something like that? So that is our main question now. Uh, well, one thing that we can notice is we really want 1 minus a to the minus first to be equal to something that has to do with 1 minus p, right? Because in the standard in the normal in the standard parametrization of the binomial distribution, the probability of attaining 0 is equal to 1 minus the success rate to the n. So we want to find out what p is in our case by considering that 1 minus a to the minus first is equal to 1 minus p. And this implies that 1 minus p multiplied by 1 minus a, well, should be equal to 1. And if we do a bit of rearranging, then we can arrive at the fact that then a should be equal to p over 1 minus p. And I mean, then we can recognize as well that p is equal to a minus 1 divided by a. So this is the version of p that we have. And if we plug this thing inside here, then we get the version of the binomial distribution that we had earlier. And we can just for the sake of fun, try to plug the a value that I get here into the qk and see what happens. So then qk will be equal to p to the k divided by 1 minus p to the k. Actually, it will be, sorry, no, it will be, I think I have to have a minus here. I forgot a minus. So a will actually be p over minus 1 minus p. Okay, so qk will then be p to the k divided by 1 minus p to the k multiplied by n choose k. And then since this is minus 1 minus p in our parametrization, we have 1 minus p to the n, and then it's equal to n choose k, 1 minus p to the n minus k, and p to the k. So we recognize here that if we choose an a and b inside the AB region for the binomial distribution, then we actually get that qk comes from a binomial distribution with parameters n and a minus 1 over a. So that was the binomial part. See you guys in the next one, where at last we can finish this very, very long exercise.